next speaker is Francisco Rodrigues from the University of São Paulo, campus of São Carlos.
Okay, thank you for the invitation. I will talk about machine learning in networks. So what I will show is how to predict disease spreading in complex networks. So basically, I will talk about what is a complex network. I will describe how to model dynamic epidemic process in networks. Then I will show how you can use machine learning to perform the prediction of dynamical process. I will show how to identify the most influential spreaders, which is really important for vaccination. And also I will give some ideas about some futures research that in the challenges we have. So what is a complex network? In a network, we have a graph. A graph is a set of nodes. So you have here a set of individuals. These individuals are connected according to friendship, like in Facebook, for example. And then we mathematically represent this structure as a graph. In a graph, you have a set of nodes connected by edges. So you have examples of networks in our society when you have people connected according to friendship or familiar ties. We have a network in our brain when you have neurons connected by synapses, and also in the cortical level when you connect different regions according to activity. Another example is the internet, when you have computers connected by physical connections. Like, for example, here you have the internet in the beginning. So this network emerged, and now you have a very big network. So you have networks everywhere. We have networks in the Facebook, internet, proteins, airports, scientific collaboration, several different networks. And the idea is to study the structure and the function of networks. So we want to describe the network structure and try to understand how this structure affects dynamical process. So to study networks, we have three different fields. We have the structure. When we wanted to describe the network structure, we wanted to find patterns of connections inside the network. We have dynamics, when you simulate dynamical process in networks like epidemic spreading, synchronization, and you want to verify how these network structures will influence the dynamical process, and also have applications. When you use networks in medicine, biology, in different areas to try to understand the system. So to describe the network topology, we need to use some metrics, okay? So here you have this network. If you take a look on this picture, you cannot extract any useful information. So to describe network structure, we need a set of network measures, and to extract these measures, we need to represent the network as the adjacency matrix. The adjacency matrix, we have the elements will be 1 if you have a connection, for example, between node 1 and 2. So you have a connection here, so the element is 1. And is 0 if you do not have the connection. From the adjacency matrix, we can extract the number of connections of each node. For example, this node has 2 connections, this one has six connections. And from the degree, we can extract the degree distribution, and the degree distribution can be used to describe the network organization. For example, we have here the degree distribution of a purely handled network. Here we have the degree distribution of a scale-free network. The scale-free network is a network in which we observe in our society. And in this case, we have that most of the nodes have only a small number of connections, but we have a small set of nodes that are densely connected. Another important measure to describe the network structure is the distance. In the distance, we have that is the number of connections that we have between 2 nodes. For example, in this case, we have the connections between, the distance between Anne and Paul is used to 3. And also, we have centrality measures. Centrality measures are really important because we want to identify the center of the network. If you can identify the center of the network, then we can try to vaccinate these nodes in order to stop some outbreak, for example, because we expect that if a node is at the center of the network, this node will spread information easier than the nodes that are at the border. Okay? So different centrality measures will give you different results. So this is a big problem we have in network. So the question is how to select these measures to associate the network structure with a given dynamical process. So I have many different measures, like it's related to the spectrum of the network, based to entropy of different measures, centrality, subgraph, and many others, okay? And after describing the network structure, we can use this structure to try to infer the evolution of the dynamical process. For example, we can analyze the resilience of networks from the structure of the network, epidemic spreading that we'll talk today, rumor spreading when you have information that is propagated in a social network. We have random walks, synchronization, and many others dynamical process. And in the case of the networks, the epidemic spreading, the question is how the network structure will influence the propagation of a given disease. So given that this guy is infected, how many people will be infected? Okay, can we predict this number of cases from the network structure? Just to show the influence of the network, here you have the propagation of bubonic plague in the 4th century. So to go from Turkey to Sweden, it took about 4 years, okay, because people in that time usually could not move so long as today. And to compare with the cases we have nowadays, this is the 2009 pandemic flu. In just 3 months, the disease started in Mexico and spread it to all the continents in just 3 months, okay? So what's the difference between these two cases is the network structure. Because today we can, for example, from here today, we can travel from here to China in just 1 day, okay? And take the disease from here to there in some hours, okay? So the question is, can you quantify this dependence of the network structure with the number of cases that you can measure in a network? So to do this, we have to model the epidemic process, and this is the classical case. We have one susceptible individual will become infected and can become susceptible again, so we have SIS. We have SIR, if you have immunity, okay? So following these states, we have different models. We can model SIR, SIS, and many others. And to solve this modeling networks, we needed to use some approximation, okay? So this is degree-based mean field approximation. And what to do in this approximation is to assume that the fraction of infected nodes with degree k, with k connections, depends on the interaction between susceptible individuals and infected individuals. This terms here is given by the network structure because these terms will give the probability that, given that a node is susceptible, and if you follow one link of this node, this is the probability to get to arrive in an infected node at the other end, okay? So after writing this equation, we can use a first-order approximation. By the first-order approximation, we can calculate the characteristic time, and from this time, we can calculate the critical threshold for the propagation of the epidemics. So after reaching this threshold, we have the epidemic phase, so the disease will propagate. Otherwise, the disease will not propagate, okay? And here is really interesting because this critical threshold where you have the phase transition depends on the network structure. So this is the average number of connections. This is the second moment of the degree distribution, okay? So if you have a network in which this term is larger, then it is easier to propagate the disease, okay? So if you compare here a scale-free network with a random network, we can see that for a scale-free network, the second moment of the degree distribution will be very large, and in the limit of infinity, a network with infinite size, this will diverge, so this is really close to 0. Then, in your society is a kind of scale-free network, then we have that one disease will spread easily in your society, so you have a lot of cases in short time, okay? Just to show another kind of modeling here, we developed a model in which you have epidemic spreading with awareness, okay? So for example, if you have one disease propagating in a given society and you know that this disease is propagating, we can try to change or the way that we wash our hands, for example, to try to avoid the disease, okay? So the idea is, in this model, we have 2 layers. In one layer, we have a social network like Facebook or Twitter, for example. So this is, in this layer, the propagation of information. We have the propagation of information, okay? In the another layer, we have the physical contacts, okay? It's the physical contacts between people. So in this case, we have 3 states, susceptible, infected, and susceptible, but also we have states related to the information, okay? So you have that one individual can be ignorant when you do not know about the disease, okay? So you can be susceptible and ignorant, so you don't have the disease and you don't know about the disease. Susceptible and spreader. Spreader is someone who knows the disease, about the disease, who knows the information, and you propagate the information. A SAIFR is someone who knows the information but will not propagate, okay? So you have different states. From these states, you can write the model, okay? And here, just to understand the influence of the information, we put here a probability that at each time step, I will propagate the information with probability pi, and the disease with probability 1 minus pi, okay? So for example, if pi is 1, I propagate only the information about the disease. If it's 0, I propagate only the disease, okay? So this is what we want to analyze. We verified that if you increase the velocity of propagation of the information, we always decrease the prevalence, the number of cases, okay? It is expected. But we verified something interesting here. When you put one case that, for example, I am infected, and I do not inform other people that I am infected, okay? It's like, for example, in sexual diseases. For example, infected, and if you're not informed, what you see is this, okay? If you increase the velocity of propagation, the number of cases will increase, okay? So in this case, we are informing our society, for example, about the disease, but if people do not propagate the information that these people are infected, we have an increase in the number of cases, okay? This can explain, for example, the number of cases of sexually transmitted diseases in the US, okay? So you can see that the network structure and also the velocity of propagation on information is fundamental to understand how one disease will propagation in a given society, okay? So this is our last paper about explaining different ways to model disease propagation in single layer and multi-layer networks. So that we know that epidemic spreading depends on the network structure, okay? So we verified in different ways for several different models. So one question is, can you predict this dynamical process, okay? So in this case, what you do is consider this hypothesis, okay? So you have the propagation of a given disease, and you assume that this is a function of network structure, okay? Plus one error is this is something that you cannot, we don't know or you cannot measure, okay? So in this case, we have a kind of regression because we have the number of cases will depend on the network structure, but this function is really complicated because in a given network, the complex network are very heterogeneous, okay? We also have feedbacks. We have effects related to stochastic simulation, several different effects. So one solution is to evaluate this function by use machine learning, okay? So what you do here, instead of consider just traditional statistical methods, you use methods from machine learning, okay? So how do you perform this analysis? We have the network, okay? So from the network, we will extract a set of features, like, for example, the number of connection. This is a probability that two nodes will, for example, this is the probability to find some triangles, like this one, around each node. This is a centrality measure related to the number of paths we have between two places in a network. For example, in this case, for example, this guy, if I remove this guy, I would disconnect the network in two parts. So this guy is really important. This is called between centrality. Here you have the page rank, which is related to the number of random walks we have a network that will visit each node. Here is the key core, and this is again centrality related to page rank. And we assume that our target variable is the number of cases. Okay, so this is the number of cases you have. And then we perform the simulation, and we collect the number of cases that each node will infect. For example, assuming that I am infected, how many people will be infected? Okay, I will infect how many people after a long time? This is the idea. So to evaluate this function, we consider random forest algorithm and the neural network. Just to give an overview about a neural network will have a number of entries in which you have the attributes we put here. Then the attributes will be transmitted from one layer to another layer. Then we try to adjust the weights of the network, the neural network, according to the error in the prediction. Okay? So after performing this kind of optimization, we can try to predict the output, okay? And we also consider the random forest algorithm. The random forest algorithm is a way to improve the accuracy of decision trees, okay? So what we do is we have a set of n elements. From these n elements, we perform a sample, and from each sample, we construct a decision tree, and then we construct several decision trees, and after this, we combine these decision trees in order to find the solution. Okay, so this is a kind of bagging in which you have a data set, construct several decision trees, and you use several decision trees to improve the prediction and decrease the variance in the output. Okay. To perform the regression, we have a training set and a testing set. So you have our data set we divide in two parts. One part is to train the model. Another part is to test the model. So this training set will be used to adjust the neural network or the random forest. And then we evaluate our model by using the testing set. Okay, so this is the result for two different networks. We can see that for the US transportation network, this is the data, this is the prediction, and you can see that you can predict very well how the network structure, because we can predict very well the number of cases from the network structure. So you can see that the network structure contains a lot of information about the disease propagation. Okay, so we need to use this network structure to try to infer the number of cases. Another problem we can evaluate by using machine learning is the identification of the most influential spreaders. We know that in our society, some people are more important than other ones, okay? And in the case of epidemic spreading also, we have some people that will propagate easier than other ones. We also have the same structure in the case of airports. Some airports are more important than other ones. So for example, if you have one infected person here is more critical than to have one in El Paso, for example. So one question is, can you identify the most important nodes from the network structure? So we, for example, can you identify the most influential spreaders by just taking a look on the network structure? We have that most complex networks are very heterogeneous, okay? So the structure are very heterogeneous, so you have that a small number of nodes are densely connected, okay? Much more connected than the other ones. So if you have heterogeneous structure, we have some nodes that are more important than other ones. So you assume that important nodes are the central nodes, okay? But centrality, we can quantify in different ways. This is a big problem. So if you consider just one centrality measure, for example, we can see that here we have, for example, the degree, and here is the number of cases that each node will infect if the disease is started in that node. For example, I am infected, how many people are we infected after a given time, okay? We can see that if you consider each measure individually, we cannot get very good correlation, okay? So this is really complicated. We also proposed a new measure called random walk accessibility. And in this measure, we can try to identify the center of the network. This is based on the adjacency metrics. It's a kind of random walk in which you have a fitness associated to each node. And if the fitness decreases when you perform the random walk, we have this kind of random walk accessibility. And if you plot the random walk accessibility versus the number of nodes that are infected, we can get a better correlation, but it's not perfect yet, okay? So this is a big question is, what is the best centrality measure to try to identify the most influential spreader? We can see that you can get similar results in different networks, so the result does not depend on the network structure. We also compare this accessibility with different metrics, and we got a better correlation than the other cases. But this is the problem. We have different centrality measures, and you want to perform the prediction, the identification of the most influential spreaders, and we don't know which one is the best option to select these spreaders, okay? So again, we assume that the prevalence depends on the network structure. Then you use the random forest algorithm to perform the regression again. When you use the random forest algorithm, there is something interesting because the root of the decision tree will give me the importance of each attribute. Because if you want one attribute is selected several times, it implies that this attribute is very important, okay? So in this case, you can quantify the importance of each measure. And we verify that it's not possible to identify the most influential spreaders by using just one measure. We needed to combine several different measures to try to perform this identification, okay? And also, we verify that the importance of each measure depends on the network structure. For example, for the airport network, the key core is not so important as in the case of social network. Okay, so the importance of each measure depends on the network structure. Okay, so this is the problem. So if you wanted to identify these nodes, instead of using just one measure that people usually do, we need to combine. Okay, so what you conclude from these preliminary results is that machine learning can be used to infer, to predict the number of cases in disease spreading, okay? But you have many challenges, okay? For example, how to predict disease propagation from the network structure? We select a set of measures, okay? Like, for example, 10 measures, but we can extract much more, okay? And we need a method to select which measure we put in your model to try to improve the accuracy, okay? The modality of temporal interactions, because we have a complex network, in your case, we have a static structure. So if you wanted to have something more realistic, we needed to use temporal interactions, okay? In this case, we can also use machine learning to try to predict the evolution of the network. Multi-layer organization is also important. When you have, for example, in this case, we can have a network in which you have, for example, airplanes, we have airports, we have roads and highways, and also subway, okay? So people can move from one medium to other ones, and then we can model this network from several layers, okay? So you have one layer from airports, one layer for highways, one layer for subway, for example, okay? Host heterogeneity is really important because in your model, we assume that all the nodes are similar, okay? So they have the same properties in the same capacity of propagation. And also, it's important to develop methods to control the disease propagation, okay? So in this case, we can try to simulate in a given network which nodes I will select to put in quarantine or to apply the vaccination in order to decrease the number of cases, okay? And also, the number of influential spreaders is also a big problem because now we need to know the network structure to identify these most influential spreaders. But one question is, if you don't know the network structure, and we know, for example, just the number of cases in a small part of the network, can you try to infer the whole network structure from these influential spreaders? So this is something we are trying to do with machine learning, okay? So this is all, okay.
Thank you. So questions?
Yeah.
Thank you very much for
Okay, thank you.
Very, very interesting. I would like to ask you to please go back to the slide where you show about the pie chart.
Okay.
I have a question about the conception about this.
Okay, yeah.
Yeah. Please, just correct me if I'm wrong.
Uh-huh.
But what I understand is, according to what you said, someone who the information spreading and the disease spreading is not cannot be mutual together.
Yeah,
But
yeah.
I can't understand this because I suppose it's possible to consider both together, isn't it?
Yeah, but here we assumed a discrete time simulation. Okay, so at each time step, we consider the propagation, the information, or the disease. But it's possible to model in a continuous time. This is just to facilitate the solution of the questions.
Okay, so
Yeah.
it not means the individual can't propagate both separately.
Yeah, no, just one. Yeah, we just assume this in your model. Yeah,
Okay,
but it's possible to consider this case.
Okay, thank
Yeah.
you very much.
Nevertheless, I think the idea is perfect for sexual disease.
Yeah. Because you can be infected in you do not, people do not know you're infected. Yeah.
The problem I see is how to build network with real data.
Yeah.
Yeah, it's beautiful. You can apply
Yeah,
all
yeah.
these methods, but it's very hard to from Brazilian data to build networks to do such a thing.
Yeah, indeed, it's possible to collect. For example, there are some data sets in which people put some sensors in students and verify how the students interact. Okay, or it's possible, for example, you put in your cell phone one software in which, for example, you identify if you are interacting. So this is something that needed to be collected, yeah, but it's not possible today. Yeah.
So in terms of travel restrictions, especially now for coronavirus, do you think that it has to be focused on airports that have the most connections, or are there other properties within the network that would make sense to implement?
Yeah, this is a good question because, for example, you can have a network in which you have a network that is at the border. For example, it's very connected, but it's at the border of the network. For example, you have the network is here.
So you think that betweenness is more important than degree?
It depends on the case. For example, in this case, the degree is not important because we have the hub at the border of the network. Okay, but the betweenness is a problem also because in betweenness you can have like this one that has just two connections. Okay, so the best is try to combine several ones. Like, for example, you define one metric that you use degree, betweenness, page rank, eigenvector centrality, all together. This is the best option.
Have you done that for the U.S. airline network?
No. What you do here in your case is try to combine all these different metrics in just one function. For example, here, for example, when I put the network structure, what we included there is several different centrality measures.
Yeah,
Okay.
did you rank the airports by this combination?
No, no, but it's possible. Yeah,
Okay.
yeah.
One very good example, as you said, for this model is the spread of sexual
Yeah.
You are considering here static networks,
Yeah.
right?
Yeah.
And then very likely they are not static.
Yeah.
And taking one example here in Brazil, let's say you have your network and then you have Carnival.
Yeah. So,
And then
yeah.
you come back. So have you tried to infer if this changing the network would change your predictions or make it better?
Indeed, it's possible to include in this model because this model considers a static network. But for example, what you can do is divide the time discretely and include for each time you put one network. Okay, and then you combine use the same approach to combine all the data you have. Okay, so it's possible, but the problem we have today is how to define the dynamic of the connections. Because, for example, we are connected, but what's the final connection? So this is just indeed this, our paper is the first one to consider machine learning in epidemic spreading in networks. So we expect that from now, people will propose other models and try to improve the models to consider more realistic cases. Yeah.
So can I just make a comment that in
Yeah.
terms of data for networks, you could use Wikipedia, and so if you take articles and then
Yeah.
all the links within the articles are connected, you can create, and Wikipedia releases all the data free of charge. So
Yeah.
anyone can create a network based on different topics. That's just something that it's available to the community.
Yeah. Indeed, what you can do is use Facebook as one approximation for social network.
Well,
So
yeah,
this is
but
possible.
Facebook
Yeah.
is very restrictive in terms of sharing data.
Yeah.
So, but yeah, obviously we do want networks of real population because we want to model disease spread.
Yeah.
That's a limitation, but.
Yeah. This limitation we have.
Any more questions? So, thank you again.
Thank you.
So, now we will have a very long break until 5:30.